Most of our universe is made of something we cannot see. This invisible substance, called dark matter, is the cosmos's hidden architect, sculpting everything from the smallest galaxies to the vast cosmic web. For decades, its ghostly nature has challenged our fundamental grasp of reality. By the end of this journey, you will understand how this unseen force dictates the fate of our universe and why its discovery would rewrite the laws of physics. We will investigate why galaxies don't fly apart and how scientists are hunting for a particle that refuses to be found. What does it mean for our reality that the majority of it is permanently hidden from our view in the quiet halls of a Swiss observatory during the 1930s? An astronomer named Fritz Zwicky made a calculation that shook the foundations of physics. He was studying the Coma cluster, a vast collection of galaxies bound together by gravity, and he found a glaring inconsistency. When he added up all the visible mass from the stars and glowing gas, the total was far too small. The gravitational glue holding the cluster together needed to be immensely stronger, suggesting the presence of something unseen. He called it Dunkel Materie, dark matter. This was the first time the cosmic missing mass problem was formally identified, revealing a universe where the books simply did not balance. The evidence only grew stronger decades later with the meticulous work of Vera Rubin. She measured how fast stars orbit the centers of spiral galaxies, expecting the outer stars to move more slowly, just as Pluto orbits our Sun much more sluggishly than Mercury. Yet her data revealed a stunning truth. Stars at the very edges of galaxies were whipping around just as fast as those near the bright core. The only plausible explanation was a massive, invisible halo of dark matter enveloping each galaxy, providing the extra gravitational pull to keep these fast-moving stars from flying off into the void. These observations forced a humbling admission. The cosmos we see, the glittering tapestry of stars and galaxies, is merely the visible embroidery on a hidden fabric of dark matter. This unseen substance dictates the motion of everything we can see, a silent partner in a cosmic dance. So if dark matter's gravitational influence is so undeniable, what could this mysterious substance possibly be made of? Think of a spinning tire flinging mud off into the air. Now picture a galaxy, a colossal wheel of stars spinning at incredible speeds. If a galaxy were only made of the stars and gas we can see, the very same thing would happen. The outer stars, whipped around by the rotation, would simply fly off into the emptiness between galaxies. They do not. They remain tethered to their cosmic home, and the reason is the invisible hand of dark matter. Every galaxy we observe is cocooned within an immense, unseen halo of this mysterious substance, a halo that stretches far beyond the galaxy's visible edge. This dark matter provides the crucial extra gravity, the invisible glue that holds the entire structure together. We see the proof in what astronomers call flat rotation curves. When scientists chart the speed of stars orbiting a galaxy's center, they expect the outer stars to slow down, just as distant planets in our solar system orbit the Sun more slowly. But the data reveals something astonishing. Stars far out in the galactic suburbs whip around just as fast as those near the bright downtown core. This can only mean one thing. An enormous amount of unseen mass must be present, its gravity gripping those high-speed stars and preventing the galaxy from tearing itself apart. This is the first and most fundamental role of dark matter, that of a galactic architect. Without its hidden scaffolding, the beautiful, stable spirals we see through our telescopes would simply not exist. They would be fleeting, chaotic swirls of stars, quickly dissolving into the cosmic background. But dark matter's influence does not stop at the edges of individual galaxies. This invisible substance is also the master builder of the largest structures in the entire universe. The grandest structures in the cosmos owe their existence to this invisible sculptor. If you could pull back to view the entire observable universe, you would not see a random scattering of galaxies. Instead, you would witness an intricate architecture, a vast cosmic web of brilliant filaments and dense nodes, all separated by unimaginably large, empty voids. This is the universe's large-scale structure, and its primary architect is dark matter. In the earliest moments after the Big Bang, the cosmos was a nearly smooth soup of particles. But within this soup, dark matter held a crucial advantage. It does not interact with light, so the intense pressure from radiation in the young universe could not push it away. This allowed tiny, random ripples in the dark matter, slight variations in its density, to act as gravitational seeds. Over billions of years, gravity relentlessly pulled more and more dark matter into these dense spots. This dark matter scaffolding grew first, forming an invisible skeleton across the cosmos. Ordinary matter, the atoms that make up stars and planets, was then drawn in by the immense gravitational pull of these dark structures. Galaxies formed at the intersections of these invisible filaments, and immense clusters of galaxies gathered at the densest nodes. Supercomputer simulations, like the famous Millennium Run, tell this story with stunning clarity. When scientists program the laws of physics and let a universe of only dark matter evolve, the simulation spontaneously generates a cosmic web that looks exactly like the one we observe. This reveals a profound truth. The glittering galaxies we see are just tracers, tiny pinpricks of light outlining a hidden framework built by dark matter. Without its gravitational blueprint, the universe would lack its rich structure. It would be a far more uniform and lonely place, a sparse, dim sea of gas with no grand clusters, no brilliant filaments, and likely no life. How then can we possibly map the distribution of something that emits no light at all? The very fabric of space itself betrays the presence of the unseen. When light from a distant, brilliant galaxy travels across the cosmos toward us, its path is not always straight. If its journey takes it near a massive object like a foreground galaxy cluster, the fabric of space-time warps around that immense concentration of mass. The light follows this curved path, bending around the obstacle like a car following a curved road. From our vantage point, the image of that background galaxy can be stretched, magnified, or twisted into multiple images or brilliant arcs of light. This phenomenon, called gravitational lensing, is nature's own magnifying glass, and it gives us a powerful tool to weigh the invisible. The amount of bending we observe depends directly on the total mass causing the warp. Since the visible stars and gas account for only a tiny fraction of the needed mass, the rest must be dark matter. This technique allows us to literally map the distribution of something we cannot see by watching how it distorts the light from objects behind it. One of the most stunning demonstrations of this comes from a violent cosmic collision known as the Bullet Cluster. Here, two enormous clusters of galaxies have slammed into each other at immense speeds. During such a collision, the clouds of hot, glowing gas that fill the clusters, the ordinary, visible matter, crash into each other, slow down, and get stuck in the middle due to friction. The dark matter, however, does not interact with this gas or with itself in any significant way aside from gravity. It is effectively frictionless, so when astronomers mapped the mass using gravitational lensing, they found something extraordinary. The bulk of the mass, the dark matter, had simply sailed right through the collision and now resided in two separate blobs on either side of the pile-up of hot gas. This was a direct visual proof that dark matter is not just hidden ordinary matter. It is a fundamentally different substance that interacts through gravity alone, a ghostly presence revealed only by its gravitational shadow. Across the universe, astronomers now use both strong and weak gravitational lensing to conduct cosmic inventories. Strong lensing creates those dramatic, giant arcs and multiple images, while weak lensing produces subtler, more widespread distortions in the shapes of millions of background galaxies. By carefully analyzing these tiny twists and shears, scientists can create detailed mass maps of vast regions of space. These maps consistently reveal the same story. The halos of dark matter surrounding galaxies and clusters are immense, stretching out far beyond the last visible star, and they contain many times more mass than all the luminous matter combined. Through this cosmic trick of light, we are able to trace the invisible skeleton of our universe, confirming that dark matter is not a minor component but the dominant architectural force, its gravitational hand guiding the formation and fate of everything we can see. So if dark matter's gravity sculpts the cosmos, what is this invisible sculptor actually made of? This question lies at the heart of a modern scientific detective story. We know what it does, but we have no idea what it is. The leading hypothesis points to an entirely new class of particles, ones that do not belong to our standard model of physics. The most famous candidate is called a WIMP, which stands for Weakly Interacting Massive Particle. As the name suggests, these theoretical particles would have significant mass and interact with ordinary matter only through gravity and perhaps the weak nuclear force, the same force responsible for radioactive decay. This feeble interaction is precisely why they are so elusive, passing through our planet and our bodies by the trillions every second without a trace. The appeal of WIMP is that their theoretical properties, forged in the intense heat of the Big Bang, would naturally produce the exact amount of dark matter we observe in the universe today. It is an elegant solution, but it remains unproven. Other intriguing ideas compete for attention. Axions are another hypothetical particle, conceived to solve a different puzzle in particle physics, but they could also constitute dark matter. They would be incredibly light, potentially streaming through space in vast, wave-like rivers. Some scientists wonder if dark matter could be made of sterile neutrinos, a heavier, more aloof cousin of the regular neutrinos that flood the cosmos. There is even the possibility that it consists of primordial black holes, ancient relics formed from density fluctuations in the universe's first frantic moments. Each candidate carries radically different implications. Finding a WIMP would open a whole new chapter in particle physics, while confirming Axions would reshape our understanding of fundamental forces. This diversity of ideas highlights the core of the mystery. Dark matter does not emit, absorb, or reflect light, and it seems to ignore the electromagnetic force entirely. It does not bump into atoms, it does not clump together to form dark planets, and it barely, if ever, notices itself. How do you hunt for something so profoundly ghostly? The search requires monumental ingenuity, pushing our technology to its absolute limits. This puzzle brings us to one of the most profound mysteries in all of physics, a problem so deep it challenges our very understanding of reality. Known as the hierarchy problem, it asks a deceptively simple question. Why is gravity, the force that holds entire galaxies together, so unimaginably weaker than the other fundamental forces? The weak nuclear force, for instance, is a trillion times stronger than gravity. This is like comparing the power of a single mosquito to the combined energy of every star in the observable universe. Such a vast difference seems unnatural, almost as if the universe is deliberately fine-tuned in a very precarious way. physicists have long sought a more elegant, natural explanation, and one of the most beautiful ideas to emerge is called supersymmetry. This theory proposes a profound and hidden symmetry in nature, where every known particle we have discovered has a secret, super-heavy partner. The electron would have a selectron, the quark would have a squark, and the photon would have a photino. This elegant doubling of the cosmic roster of particles would provide a neat solution to the hierarchy problem, stabilizing the mass of the Higgs boson and making the vast gap between gravity and the other forces feel less like a bizarre accident. But there is a breathtaking bonus hidden within this theory. The lightest of these new supersymmetric particles, often called the lightest supersymmetric particle or LSP, would be completely stable. It would have mass, but it would not interact with light or ordinary matter through the electromagnetic or strong forces. It would be neutral, stable, and virtually invisible, passing through the cosmos like a ghost. In other words, supersymmetry naturally and elegantly predicts the existence of a perfect dark matter candidate. This theoretical particle would have been forged in the immense heat of the Big Bang, a relic from the universe's first moments that simply never decayed away. Calculations show that if such a particle exists, it would be produced in just the right abundance to account for all the dark matter we observe in the cosmos today. It is a stunning convergence where the solution to one deep puzzle in particle physics appears to solve the greatest mystery in cosmology. The hunt for this particle, a WIMP born from supersymmetry, has driven decades of experimental effort. Yet, despite its compelling beauty, nature has so far kept its secrets. Powerful particle colliders like the Large Hadron Collider have not yet found any direct evidence for these super-partner particles. This does not kill the idea, but it pushes the possible masses of these particles to higher, more elusive energies. The enduring appeal of supersymmetry lies in its power to tie up so many loose ends with one elegant concept. It illustrates a crucial point in our search for dark matter. We are not just hunting for a single missing ingredient. We are searching for a more complete theory of reality, one where the invisible hand shaping the cosmos is intimately connected to the fundamental laws governing the smallest scales of existence. With the most elegant theories still awaiting confirmation, scientists have been forced to widen the hunt, exploring a breathtaking array of alternative possibilities that are, in their own ways, even stranger. But what if we have been asking the wrong question this entire time? The hunt for a missing particle is not the only path forward. A small but determined group of physicists proposes a radical alternative. Perhaps nothing is missing at all, and instead our understanding of gravity itself is incomplete. The leading contender in this bold rethinking is known as modified Newtonian dynamics, or MOND. This theory suggests that Isaac Newton's famous law of gravity, a cornerstone of physics for centuries, breaks down under certain conditions, specifically in the extremely weak gravitational fields at the outer edges of galaxies, where the acceleration from gravity is incredibly faint. The force of gravity may actually behave differently than our equations predict. It would become stronger than expected. Proponents of MOND argue that this single adjustment can perfectly explain the flat rotation curves of galaxies without needing to invent a single particle of dark matter. The stars on the outskirts move so fast because the gravitational pull from the galactic core, according to this modified law, is simply stronger than standard physics would allow. For some galaxy observations, MOND provides a remarkably clean and elegant fit. Yet for all its appeal in explaining galactic rotations, this alternative theory faces monumental challenges of its own. It struggles profoundly to account for the bullet cluster, where gravitational lensing clearly shows that the majority of the mass has become separated from the visible matter. If gravity were merely modified, how could the lensing effect be centered on regions of empty space, far from any visible gas or stars? MOND also has a very difficult time explaining the intricate patterns seen in the cosmic microwave background, the afterglow of the Big Bang. The precise fluctuations in this ancient light are a perfect match for a universe dominated by dark matter, providing a detailed blueprint that standard MOND cannot easily replicate. This ongoing debate is not a weakness in science, but rather its greatest strength. It is the sound of competing ideas being tested against the harsh judge of observational data. The very existence of these alternatives, like MOND, pushes the dark matter hypothesis to be better, more precise, and more predictive. It forces cosmologists to ensure that their invisible sculptor is not just a convenient ghost, but a necessary component of a coherent cosmic theory. This rigorous competition ensures that our final answer, whatever it may be, is built upon the most solid foundation possible. The search continues on multiple fronts, with some scientists building ever more sensitive detectors to catch a dark matter particle, while others refine the equations of gravity, attempting to build a better MOND that can explain the entire cosmic picture. This parallel pursuit, this tension between the seen and the unseen, is how we truly probe the limits of our understanding, inching closer to a final theory that can explain the full, magnificent scope of our universe. To settle this cosmic debate, we must journey back to the very dawn of time, to a moment frozen in light. About 380,000 years after the Big Bang, the universe underwent a profound transformation. It cooled enough for the first stable atoms to form, turning from an opaque, searing fog of particles into a transparent expanse. In that instant, light was set free, and it has been traveling across the cosmos ever since. We detect that ancient light today as a faint, cold glow that permeates all of space, the cosmic microwave background. This is not just any light. It is the universe's first baby picture, a snapshot of its infancy. And etched into this image are tiny, telltale variations, minuscule differences in temperature, mere millionths of a degree. These fluctuations are the seeds of all future structure, the blueprint for everything to come. By mapping these patterns with exquisite precision, satellites like Planck have given us a powerful tool to take an inventory of the entire cosmos. The way these hot and cold spots are distributed across the sky, their specific sizes and clustering, acts like a cosmic barcode. When scientists scan this barcode, the data reveals an undeniable truth. The patterns we see only make sense if a significant amount of dark matter was present, pulling on the young plasma with its gravity. Ordinary matter alone simply cannot produce the precise statistical signature we observe. The cosmic microwave background requires that dark matter outweighs normal matter by a factor of about 5 to 1. This relic radiation is the ultimate arbiter, a fossil record that confirms dark matter was not a later addition. It was a fundamental ingredient in the primordial universe, a necessary component from the very first moments. This evidence is so compelling that it forms the bedrock of our standard model of cosmology, known as the Lambda CDM model. In this framework, dark matter is not a speculative idea. It is the invisible backbone upon which the entire visible universe was built. Its gravitational influence in that early epoch dictated how quickly galaxies could form and how the vast cosmic web would eventually take shape. Without it, the universe we see today would be fundamentally different. The cosmic microwave background provides a critical, independent line of evidence that beautifully corroborates what we see in galaxy rotations and gravitational lenses. It tells us that the invisible sculptor was there at the beginning, quietly laying down the foundations for the grand cosmic cathedral we inhabit today. Deep underground, in the profound silence of abandoned mines and mountain tunnels, a new kind of astronomy is taking place. Scientists are not looking up at the stars, but down into vats of ultra-pure liquid xenon, waiting for a ghost to bump into an atom. This is the frontier of direct detection, a high-stakes effort to feel the unfelt. These experiments, with names like LUX Zeppelin and Xenon NT, are technological marvels designed for one purpose: to register the infinitesimal recoil of an atomic nucleus if it is ever struck by a dark matter particle. The core of these detectors is a large tank filled with tons of liquefied noble gas kept at frigid temperatures. The environment is kept in total darkness, a perfect void, because any signal they hope to see would be far fainter than a single photon of light. If a WIMP, one of those hypothetical dark matter particles, were to pass through and actually interact with a xenon nucleus, the collision would produce a tiny flash of light and a wisp of free electrons. Sophisticated sensors lining the tank would capture these twin signals, pinpointing the energy and location of the event. The challenge is almost beyond comprehension. Trillions of these particles are likely streaming through the Earth and through these detectors every second. Yet their interactions are so incredibly weak that a collision with an atom might only happen a few times per year in a ton of material, if at all. To have any hope of seeing such a rare event, every possible source of interference must be eliminated. This is why the detectors are buried under a mile of solid rock, which acts as a shield against the constant rain of cosmic rays from space. The materials used to build the detectors themselves are meticulously chosen for their ultra-low natural radioactivity. Even with these heroic measures, the search is like trying to hear a single, specific whisper in a stadium full of people all talking at once. The background noise from subtle radioactive decays in the surrounding rock and even in the detector components creates false signals that must be painstakingly identified and filtered out. So far, after years of data collection with increasingly sensitive instruments, no definitive, unambiguous signal has emerged. The detectors have remained quiet. Yet in this field, a null result is not a failure. Every experiment that finds nothing helps to rule out vast swaths of potential territory. Each new, more sensitive detector tells physicists what dark matter is not, shrinking the possible hiding places and tightening the constraints on its mass and how strongly or weakly it interacts. This relentless process of elimination is slowly painting the invisible sculptor into a corner. While one branch of science listens in deep silence for a whisper, another tries to create the mystery particle from scratch. Another approach listens for the death cries of dark matter itself. Imagine if these invisible particles are their own antimatter opposites. Wherever two of them meet, they could mutually annihilate in a silent flash, converting their mass directly into a burst of energy and familiar particles like gamma rays, neutrinos, or antimatter like positrons. We would not see the collision, but we might detect the aftermath. This is the principle behind indirect detection, a method that transforms the entire cosmos into a vast particle physics experiment. Astronomers use powerful telescopes to scan regions of space where dark matter is predicted to be most densely packed. The centers of massive galaxies, including our own Milky Way, are prime hunting grounds as are dwarf spheroidal galaxies. These faint, small galaxies are thought to be overwhelmingly dominated by dark matter, making them pristine laboratories with very little astrophysical noise to confuse the signal. Instruments like the Fermi Large Area Telescope tirelessly map the gamma-ray sky, searching for any unexplained glows or excesses of radiation that cannot be accounted for by known objects like pulsars or black holes. A key signature would be a specific pattern, a sharp spike in gamma rays at a very particular energy, corresponding to the mass of the annihilating dark matter particle. Over the years, a few tantalizing anomalies have emerged, like an unexpected excess of gamma rays from the galactic center. The heart of our galaxy is a crowded, chaotic place, however, bustling with pulsars and other energetic sources that could easily mimic a dark matter signal. To date, no single observation has been conclusive. Every potential signal has been matched by a plausible, conventional astrophysical explanation. This is the immense challenge of indirect detection, separating the faint whisper of a fundamental new physics process from the roaring background symphony of the universe. Yet the search continues because a single, verified signal from a quiet, dark matter-rich dwarf galaxy could be the breakthrough that finally identifies our invisible sculptor. The world's most powerful microscope is not a lens but a tunnel, a 27-kilometer ring buried beneath the French-Swiss border. This is the Large Hadron Collider, where protons race at 99.9999991% of the speed of light and then are steered into a head-on collision. In these spectacular crashes, temperatures and energies soar to levels not seen since the first trillionth of a second after the Big Bang. For a fleeting instant, the very fabric of space-time seethes with raw potential, and from that energy, new particles can blink into existence. This is the third great method in the hunt for dark matter, the strategy of creation. If we cannot catch dark matter out in the wild or listen for its death throes, then we will try to manufacture it right here on Earth. The goal is to conjure a dark matter particle directly from the immense energy of a collision. But there is an immediate and profound problem. By its very nature, this new particle would not register in the detectors. It would be a ghost at the scene of the crime, escaping without a trace. So how do you find something designed to be invisible? You do not look for the ghost itself. You look for its shadow. Physicists meticulously analyze the aftermath of each collision, adding up the energy and momentum of every single particle that sprays out from the impact point. Everything must be accounted for. In a perfectly balanced event, the total momentum should be zero, but sometimes the books do not balance. The debris flies out in a way that suggests something is missing, an invisible something that carried away a significant amount of momentum. This telltale signature is known as missing transverse momentum, and it is the primary clue that a dark matter particle might have been created and then fled the scene, ignoring the detector completely. Giant experiments like ATLAS and CMS, each a cathedral of complex electronics, are built around the collision points for this exact purpose. They are cosmic accounting machines, searching for events where the math does not add up. This search is often intertwined with the hunt for supersymmetry, looking for those heavy superpartners whose own decay could produce a stable, invisible, lightest supersymmetric particle. While the collider triumphantly discovered the Higgs boson, confirming a cornerstone of the Standard Model, the dark matter quarry has remained elusive. No definitive missing momentum signal has yet been strong enough to declare a discovery, but the search is far from over. With every upgrade and every new run at higher energies, the collider probes deeper into the unknown, attempting to forge in fire what the cosmos has so perfectly hidden. One experiment has stubbornly refused to fit neatly into this quiet narrative. Deep beneath the Gran Sasso mountain in Italy, for more than 20 years, a detector named DAMA LIBRA has been telling a story no one else can hear. Its team reports a persistent, rhythmic whisper, a signal that rises and falls with the seasons in a perfect annual cycle. Their proposed explanation is profoundly elegant. As our Earth journeys around the Sun, the entire solar system is moving through the Milky Way's vast halo of dark matter. For half the year, we are orbiting headfirst into this invisible wind, and for the other half, we are moving with it. This should cause a tiny change in the number of dark matter particles streaming through the detector, creating a slight bump in interactions around June and a dip in December. The DAMA team insists their data shows exactly this predicted modulation, a compelling heartbeat they attribute to the invisible sculptor. Yet this tantalizing claim exists in a state of profound isolation. Not a single other major experiment in the world has been able to reproduce this seasonal signal. In the quiet halls of physics conferences, this has grown into one of the most enduring and contentious puzzles in modern science. Skeptics have proposed a long list of potential mundane explanations. Could subtle seasonal changes deep underground be responsible? Variations in temperature, humidity, or even the radon gas levels in the surrounding rock could, in theory, create a background rhythm that mimics a dark matter signature. The detector itself uses sodium iodide crystals, and some have wondered if interactions from other, known particles could somehow produce this annual pattern. The DAMA team has, over the years, rigorously investigated and dismissed these potential backgrounds, standing firmly by their original interpretation. This long-running controversy is far more than a simple scientific disagreement. It is a masterclass in the rigorous, often frustrating, process of discovery at the very edge of human knowledge. A single, unverified result is not enough to rewrite the textbooks. It must be confirmed, tested, and validated by independent groups using different methods and technologies. Reproducibility is the bedrock of science, the essential filter that separates a fleeting anomaly from a world-changing truth. The story of DAMA LIBRA serves as a crucial cautionary tale, a reminder of the immense difficulty of this hunt. It highlights how easily hope and background noise can become entangled, and why the scientific community demands nothing less than overwhelming, corroborating evidence before it declares that a ghost has finally been caught. The pursuit of this mystery is now driving a new generation of experiments, using the same sodium iodide technology, but with vastly improved purity and controls, designed specifically to confirm or finally lay to rest this decades-old signal. The invisible halos that cradle galaxies are not simple, uniform spheres. They possess a deep and detailed internal structure, a hidden anatomy predicted by our most sophisticated cosmic simulations. When physicists run virtual universes inside supercomputers, modeling the gravitational dance of countless dark matter particles, a consistent profile emerges for how their density should change from the halo's outer edge to its very heart. The most famous of these is the Navarro-Frenk white profile, often called the NFW profile. This model describes a halo with a steeply rising density toward the galactic center, a sharp peak or cusp where the invisible matter becomes incredibly concentrated. It is a beautiful, mathematically elegant result that flows directly from the simple rules of gravitational collapse for a cold, collisionless fluid. Yet the universe, in its infinite complexity, often has other ideas. When astronomers look at certain dwarf galaxies, small and faint satellites of our own Milky Way, they find a puzzling mismatch. The dark matter in their cores does not appear to be densely packed. Instead of a sharp cusp, the center seems to have a much shallower, more constant density, almost like a soft, fluffy core. This is the Core-Cusp Problem, a quiet but persistent tension between the pristine predictions of theory and the messy reality of observation. How can this be? One compelling possibility is that we have overlooked a powerful force, the dramatic influence of the ordinary matter we can actually see. This is the realm of baryonic feedback. Throughout a galaxy's life, cycles of stellar birth and death inject tremendous energy into the system. Supernova explosions, the violent deaths of massive stars, act like cosmic pistons, blasting waves of energy through the surrounding gas. This can literally push and churn the inner regions of the galaxy, and through gravity's unbreakable bond, this turmoil can transfer energy to the dark matter itself. Think of stirring a cup of coffee with a spoon. The swirling motion of the liquid can gradually carve out a shallow depression in the center of the whirlpool. In a similar, though vastly more powerful way, these stellar explosions may be stirring the galactic center, gravitationally scouring out the dense dark matter cusp and transforming it into a shallower core. This idea presents a breathtakingly intricate picture of cosmic evolution. It suggests that dark matter and ordinary matter are not just coexisting, they are in a constant, subtle dialogue. The invisible sculptor provides the gravitational stage, but the luminous actors, the stars and supernova, can sometimes rearrange the scenery. Resolving the Core-Cusp problem is therefore about more than just fixing a simulation. It is about understanding the full dynamic partnership between the seen and the unseen, a relationship that ultimately decides the final shape and size of every galaxy in the sky. These faint, wispy galaxies drifting around our Milky Way are cosmic ghosts in their own right. Dwarf spheroidal galaxies are so dim that you could look straight through them with a backyard telescope and see nothing at all. Yet these seemingly empty patches of sky are in fact treasure troves of dark matter. Their gravitational pull tells us they are massively heavy, but they contain almost no stars to account for that weight. This gives them mass to light ratios hundreds of times greater than a grand spiral galaxy like Andromeda. Imagine a feather that weighs as much as a mountain, and you begin to grasp the nature of these bizarre objects. Their profound simplicity is what makes them so valuable. With very few stars and almost no messy gas, the complicated astrophysics of supernova and stellar winds are stripped away. What remains is a nearly pure ball of dark matter, a pristine laboratory where we can study the invisible sculptor in isolation. One of the most telling puzzles to emerge from these dark laboratories is known as the too big to fail problem. Supercomputer simulations of our cosmos predict that the Milky Way's dark matter halo should be swarming with hundreds of sizable subhalos, dense clumps of dark matter that are massive enough to ignite star formation. According to the models, we should see dozens of bright, substantial dwarf galaxies orbiting us. Yet when we look, we find only a handful. The most massive predicted subhalos appear to be empty, devoid of the glittering stars we expect. It is as if we calculated that a city should have 50 major skyscrapers, but when we fly over, we only see 10. Where are all the buildings? This discrepancy forces a difficult question. Are our simulations wrong about how dark matter clumps together on small scales? Or is galaxy formation simply far less efficient in these small halos than we thought, with some mechanism preventing stars from ever lighting up in the vast majority of them? The answer likely lies in the fundamental properties of dark matter itself. By carefully observing these faint satellites, astronomers can place incredibly clean constraints on how the invisible sculptor behaves. The fact that dwarf galaxies even exist as stable, long-lived objects tells us that dark matter must be cold, meaning it was moving slowly in the early universe. This allowed it to clump together efficiently, forming the gravitational seeds for these tiny galaxies. If it were warm or hot, moving at tremendous speeds, its particles would have smoothed out these small-scale structures, preventing dwarf galaxies from ever forming. Their very presence is a crucial clue. Furthermore, the exact number of dwarfs we find and their internal densities are like a cosmic fingerprint, revealing how readily dark matter packs itself into small, dense halos. As our sky surveys grow more sensitive, we are discovering fainter and fainter dwarfs, each one a new data point in this grand experiment. Every new, ultra-faint galaxy mapped is another piece of the puzzle, slowly revealing the rules that govern the vast, invisible majority of our universe. These digital universes are built from the ground up, starting with a near-uniform sea of dark matter and gas. governed by the laws of physics as we understand them. Then, with the press of a button, time is set in motion. Over billions of simulated years, gravity works its magic, pulling dark matter into a vast cosmic web. Gas flows into the densest filaments, cools, and collapses to form swirling galaxies and brilliant stars. This is the power of projects like Illustris and Eagle, virtual laboratories where entire universes are born and evolve inside supercomputers. They do not just include dark matter, they place it in the starring role as the foundational framework upon which everything else is built. The ordinary matter, the gas and stars, follows its lead, drawn into the gravitational wells carved by the invisible scaffolding. But these simulations go far beyond simple gravity. They incorporate the chaotic, powerful feedback from supernova and the supermassive black holes that lurk in galactic centers. A star explodes, and the model calculates how the resulting shockwave heats surrounding gas, preventing new stars from forming or even pushing it out of the galaxy entirely. A black hole feeds, and the simulation shows how the intense radiation and jets it emits can regulate the growth of an entire galaxy. The result is breathtakingly realistic. When scientists look at the virtual galaxies produced by Illustris or Eagle, they find spirals and ellipticals with the right sizes, the right masses, and the right chemical compositions. The large-scale structure of the cosmic web, with its filaments and voids, emerges spontaneously, matching the maps we have made of the real universe. This success is a profound vote of confidence for our entire cosmological model, suggesting we are fundamentally on the right track. Yet for all their brilliance, these digital cosmos also reveal cracks in our understanding. They struggle to perfectly reproduce the full diversity of galaxy rotation curves. Some virtual galaxies match observations beautifully, while others, created under seemingly identical rules, do not. This suggests there are still intricate details in the relationship between dark matter and ordinary matter that we have not yet captured. The simulations also continue to grapple with the satellite galaxy problem, predicting more small, dark satellites around galaxies like our Milky Way than we actually observe. Are the simulations overproducing dark matter clumps, or are we simply unable to see all the faint, starless galaxies that must be out there? This is the true value of these virtual universes. They are not just digital planetariums, they are testing grounds. A physicist can change a single variable, for instance, tweaking dark matter from being completely cold to slightly warm, or giving it a tiny ability to interact with itself. Then they can rerun the entire 13.8 billion year history of the cosmos and see what emerges. Does this new model create a universe that looks more like our own? Does it solve the satellite problem or fix the rotation curve diversity? By running these impossible experiments, we are not just watching the universe, we are playing with its fundamental rules, inching closer to understanding the true nature of the invisible sculptor. The most powerful objects in the universe are born in the deepest shadows. At the heart of nearly every large galaxy, including our own Milky Way, sits a supermassive black hole, a gravitational monster weighing millions or even billions of times more than our Sun. These colossal entities did not form in isolation. They grew within the densest concentrations of dark matter, the very cores of those immense, invisible halos. The relationship is symbiotic. The dark matter provides a deep gravitational well, a cosmic anchor point that draws in vast reservoirs of gas. This gas then cools, collapses, and forms the stars that will eventually feed the growing black hole at the center. The dark matter halo acts as the ultimate architect, setting the stage and gathering the resources, while the black hole becomes the dynamic, violent engine at its heart. This gravitational partnership goes both ways. As the black hole feeds, gorging on gas and stars, it releases phenomenal energy in the form of radiation and powerful jets. This violent outburst can heat the surrounding gas, pushing it away and effectively shutting off the black hole's own food supply for a time. But through gravity's unbreakable bond, this turmoil can also influence the dark matter itself, potentially scattering it or even carving out a shallower core in the very center of the halo. It is a constant cosmic feedback loop between the seen and the unseen. One of the most provocative ideas in modern cosmology suggests this relationship might be even more fundamental. What if some dark matter is actually made of black holes, not the supermassive giants, but countless smaller, primordial black holes? These would not be the black holes formed from dying stars, but relics from the universe's first frantic moments, born from the intense density fluctuations in the immediate aftermath of the Big Bang. If such objects existed in vast numbers, they could, in theory, constitute the invisible mass we have been searching for. The idea is beautifully simple, turning one mystery into the solution for another. Yet nature often prefers complexity. Observations have placed severe constraints on this elegant idea. If the cosmos were swarming with enough asteroid mass primordial black holes to account for all dark matter, we would see their effect through a phenomenon called microlensing. As these invisible holes passed in front of distant stars, their gravity would act as a tiny lens, briefly magnifying the star's light in a distinctive flash. Large-scale surveys monitoring millions of stars have simply not seen enough of these flashes. They rule out primordial black holes as the primary component of dark matter across a wide range of possible masses. The window is not completely closed, however. A population of black holes within a very specific, narrow mass range could potentially still be hiding in the dark, but the easy answer has been largely eliminated. This relentless process of elimination is itself a form of discovery. The intricate dance between dark matter and black holes represents a frontier where gravity is the only language spoken. By studying how stars whip around the galactic center, pulled by the combined gravity of the central black hole and its encompassing dark matter sphere, astronomers can disentangle their influences. Each observation of a flaring black hole or a wandering star adds another piece to the puzzle, helping us understand how the invisible sculptor and the ultimate abyss collaborate to build the cosmic structures we see today. Fritz Zwicky's original puzzle has only deepened with time. The Coma cluster, that sprawling city of galaxies he studied nearly a century ago, is now a textbook example of dark matter's dominant role. Modern telescopes have peeled back the layers of this cosmic giant, revealing the evidence in multiple, independent ways. The sheer speed of the individual galaxies orbiting within the cluster is the first clue. They move so fast that the combined gravity of all the visible stars and gas could never hold them together. Just like stars within a single galaxy, these entire galaxies would fly apart if something much more massive was not binding them. That something is the immense, invisible halo of dark matter in which the entire cluster is embedded. But the proof does not stop there. Look at the space between the galaxies, which is not empty at all. It is filled with a superheated gas so hot that it glows not in visible light, but in powerful X-rays. The temperature of this gas is a direct thermometer for the cluster's gravity. For the gas to be that hot, it must be confined by a tremendously powerful gravitational field, a field generated by a total mass hundreds of times greater than all the visible matter combined. This scorching intergalactic plasma provides a second, completely independent line of evidence, pointing to the same overwhelming presence of the unseen. And then there is gravitational lensing, the ultimate cosmic scale. Light from even more distant galaxies, far behind the Coma cluster, is warped and distorted as it passes through this region of space. The amount of bending we observe allows us to create a detailed map of the cluster's total mass. This map shows the dark matter not as a uniform blob, but as a vast, structured scaffold, its gravitational wells perfectly aligning with the cluster's largest galaxies. The convergence is undeniable. 3 different methods, galaxy motions, hot gas, and light bending, all tell the same story with staggering agreement. They calculate a nearly identical colossal mass, a mass that is overwhelmingly invisible. Galaxy clusters are the ultimate cosmic way stations, and their scales consistently tip toward the dark. They stand as monumental proof that the universe is built upon a hidden foundation, a framework of dark matter without which these largest of all structures would simply cease to exist. A deep crack has appeared in the foundation of modern cosmology. The universe's current rate of expansion, a number called the Hubble constant, refuses to give us a single, clear answer. When we measure it by looking at the ancient light of the cosmic microwave background, we get one value. But when we measure it using nearby supernova and other cosmic yardsticks in the modern universe, we get a distinctly different, faster rate. This stubborn discrepancy is known as the Hubble Tension, and it is more than a simple calculation error. It suggests that our standard model of the cosmos, the very recipe we use to describe reality, might be missing a crucial ingredient. This is where the invisible sculptor might be altering its work in ways we never anticipated. Could the properties of dark matter itself hold the key to this puzzle? Some cosmologists are now exploring a radical possibility. What if dark matter is not entirely passive? What if, over the eons, it has undergone a subtle evolution or interacts with the even more mysterious dark energy? Such an interaction could have gently tweaked the universe's expansion history, shifting the rate we measure today just enough to create the tension we observe. Imagine a long, slow dance between the invisible mass that sculpts the cosmos and the repulsive force that drives it apart. A slight change in their rhythm over billions of years could leave a faint imprint on the expansion rate, explaining why our 2 measurement methods no longer agree. This idea remains highly speculative, a frontier hypothesis, yet its mere existence is profoundly important. It reveals that the nature of dark matter is not a closed book. Its influence may extend far beyond simply holding galaxies together, reaching into the most fundamental dynamics of the cosmos. The Hubble tension forces us to ask whether the invisible majority of our universe is quietly orchestrating a more complex and interconnected cosmic evolution than we ever dreamed. Our cosmic destiny hinges on a silent tug-of-war between 2 invisible giants. On one side is dark energy, the mysterious force accelerating the expansion of the universe. Its opponent, the primary source of gravitational pull on the grandest scales, is dark matter. Every single particle of this unseen substance exerts a tiny, cumulative pull, acting as a cosmic brake on the runaway expansion driven by dark energy. This fundamental competition dictates everything from whether the universe will expand forever to whether it might one day collapse back in on itself. The sheer amount of dark matter and the way it is clustered throughout space directly sets the timeline for this ultimate fate. In our current best model of the cosmos, dark energy appears to have gained the upper hand, leading to the accelerated expansion we observe today. But this was not always the case. For billions of years after the Big Bang, the universe was much denser, and dark matter's gravitational grip was far stronger. The expansion was actually slowing down as the collective pull of all that invisible mass fought to hold the cosmos together. It was only about 5 billion years ago, as the universe grew more vast and empty, that dark energy's repulsive push finally overcame gravity's attractive pull. The fate of the cosmos flipped in that moment. What if the total amount of dark matter had been slightly greater? The balance would have tipped the other way. That extra gravitational braking power would have slowed the expansion more drastically, potentially leading to a big crunch, a catastrophic reversal where the entire universe collapses back into a singularity. A universe with less dark matter would have seen dark energy dominate much earlier, creating a colder, more diffuse cosmos where galaxies never had a chance to form. The precise nature of dark matter matters just as much as its quantity. If dark matter were able to interact with itself, creating a kind of dark friction, it could alter how it clusters over time. This would change the strength of the gravitational brakes in different regions, subtly reshaping the expansion's final act. So when we search for this invisible particle, we are not merely solving a puzzle about the universe's past. We are reading the first chapter of its final story, a narrative written in the language of gravity that will determine whether the cosmos ends in fire, ice, or infinite, silent darkness. The silence deep within a South Dakota gold mine is about to be shattered by a whisper, 1 mile beneath the surface, shielded from the constant chatter of cosmic rays. The LUX Zeppelin experiment is waiting. Its heart is a colossal vat containing 10 tons of liquid xenon, kept at a temperature colder than the void of outer space. This is not just a detector, it is a trap engineered to catch a ghost. LZ represents the pinnacle of a global race to directly detect a WIMP, a weakly interacting massive particle. Its sensitivity is almost beyond belief, capable of registering the faintest recoil, the slightest bump of a dark matter particle against the nucleus of a xenon atom. To achieve this, every variable must be controlled. The xenon itself is purified to an unimaginable degree, scrubbed of any natural radioactivity that could create a false signal. The entire apparatus is encased within a tank of pure water and watched over by arrays of ultra-sensitive light sensors, all designed to create a perfect dark silence. LZ is not alone in this hunt. In an Italian laboratory under a mountain, the Xenon NT experiment operates a similar xenon time projection chamber, while deep in a Chinese mine, Panda X4T conducts its own vigilant watch. Together, this global network of next-generation detectors forms a net cast into the cosmic dark, each one probing deeper into the unknown territories where our theories say dark matter should be hiding. Their goal is to explore what physicists call the parameter space, the map of possible masses and interaction strengths for the WIMP. For years, this map has been slowly filled in with negative results, ruling out vast swaths of territory. These new experiments are now venturing into the most promising, untouched regions, the places where the invisible sculptor is most likely to finally reveal a tangible form. The coming years are therefore a critical juncture. If a WIMP exists within the expected range, the steady drip of data from LZ and its cousins will almost certainly find it, triggering a revolution in physics. But if these exquisite machines also find nothing, the implications are equally profound. A null result would be a message from the universe, a clear sign that our most elegant theories are pointing us in the wrong direction. It would force a fundamental rethink, pushing cosmologists to consider even more exotic and bizarre possibilities for the nature of dark matter. The silent wait in these underground labs is not passive. It is an active and relentless interrogation of reality itself. While underground labs listen for whispers, another observatory prepares to scan the sky for the silent flash of annihilation. The Cherenkov Telescope Array, or CTA, represents a monumental leap in our ability to see the unseen through the universe's most violent light. Unlike traditional telescopes that capture starlight, the CTA is designed to detect gamma rays, the most energetic form of radiation in the cosmos. It will not look for the dark matter particle itself, but for the brilliant aftermath of its destruction. When two dark matter particles collide and annihilate, the theory goes, they should transform into a burst of familiar particles, including gamma rays carrying a specific telltale energy signature. The CTA is being built to catch that specific flash. This is not a single telescope, but a vast array of them, with one site in the Canary Islands for the Northern Hemisphere sky and another in the high Chilean desert for the Southern Hemisphere. Together, they will form the most sensitive instrument ever created for very high-energy gamma-ray astronomy, a global eye on the invisible war in the dark. Its targets are the places where the invisible sculptor is predicted to be most densely crowded. The center of our own Milky Way galaxy is a prime hunting ground, a region where dark matter should be crushed together in immense numbers, making collisions and annihilations more likely. Yet the galactic center is also a chaotic, bright place, bustling with pulsars and other astrophysical phenomena that also produce gamma rays. The CTA's incredible sensitivity and resolution will allow it to sift through this cosmic noise like never before, searching for a subtle, sharp spike in the gamma-ray spectrum that cannot be explained by any known object. It will also turn its gaze to dwarf spheroidal galaxies, those faint, dark matter-dominated satellites of the Milky Way. These are pristine laboratories with very little astrophysical background clutter to confuse the signal. If a faint glow of gamma rays with the right energy signature appears from one of these dark orbs, it could be the breakthrough we have been waiting for. The true power of the CTA lies in its ability to see a wide range of energies with exquisite detail. Imagine trying to identify a specific musical note played in a roaring heavy metal concert. Current instruments can hear the concert, but they struggle to pick out that one pure note. The CTA, with its vast collection area and advanced technology, is like a superhuman ear capable of isolating that single, perfect pitch from the cacophony. This precision is crucial because the energy of the gamma rays produced by annihilation is directly tied to the mass of the dark matter particle itself. A specific spike in the data would not just tell us that dark matter is there, it would tell us precisely how heavy it is, effectively weighing the invisible sculptor for the first time. The CTA will either find these spectral fingerprints, providing compelling, indirect evidence for specific dark matter particle models, or it will place such stringent limits on their existence that it will force us to abandon some of our most popular and elegant theories. This ambitious project embodies a fundamental truth in the hunt for dark matter. We are not just building bigger detectors, we are building smarter eyes, using the entire universe as our laboratory and its most energetic phenomena as our guide. The quiet hum of a powerful magnet could be the sound that finally breaks the dark matter case. While the search for WIMP has dominated for decades, a very different kind of ghost particle is now stepping into the spotlight. Actions are almost unimaginably light, potentially billions of times lighter than even the electron. If WIMP are imagined as hefty, solitary billiard balls, actions would be more like a vast, sloshing ocean, a single, coherent quantum field that permeates all of space. This wave-like nature is a radical departure from the particle-centric view, suggesting dark matter might not be a collection of discrete points, but a continuous, vibrating fabric underlying reality itself. The origins of this idea are not even rooted in cosmology, but in a deep puzzle within the nuclear forces that bind atoms together. Physicists call it the strong CP problem, a perplexing fine-tuning in the laws governing the strong nuclear force. The existence of the action was originally proposed as an elegant solution to this seemingly unrelated problem, a new field that would naturally restore a fundamental symmetry to the universe's laws. The breathtaking consequence was that this same field, cooling and settling in the early universe, would naturally condense into the very substance we now call dark matter. It is a stunning example of cosmic serendipity, where the answer to one profound mystery in particle physics might simultaneously solve the greatest enigma in cosmology. Hunting for this wave-like substance requires a completely different kind of trap. The Axion Dark Matter experiment, or ADMX, does not listen for nuclear recoils in a vat of xenon. Instead, it uses a powerful superconducting magnet to create an intense magnetic field. The theory predicts that within this field, an action could convert into a faint but detectable microwave photon. The experiment is essentially a supremely sensitive radio receiver, tuned to scan across millions of possible frequencies, listening for the specific whisper of an action turning into light. The challenge is to hear this one perfect note in a universe filled with radio noise. ADMX operates at temperatures colder than deep space to eliminate thermal interference, its entire core cooled to within a fraction of a degree above absolute zero. This allows it to listen for the faintest possible signal, a single quantum of microwave light that would herald the discovery of a cosmic ocean we have been swimming in all along. The rise of the action represents a vibrant and crucial expansion of the dark matter hunt. It proves that our imagination is not limited to a single, heavy particle. The invisible sculptor could be a subtle wave, a fundamental field tied to the deepest symmetries of nature, waiting to be heard through the quiet static of an impossibly sensitive magnet. Perhaps the ultimate explanation for dark matter lies not within our universe, but outside it. The Multiverse Hypothesis, a speculative but compelling idea born from string theory and cosmic inflation, proposes that our cosmos is just one bubble in an infinite, frothing sea of universes. Each of these countless realms could have its own unique set of physical laws and fundamental constants. In this grander perspective, the amount and even the very existence of dark matter might not be a fundamental law of physics. It could simply be a random, environmental outcome, a local detail in our particular cosmic bubble. We may live in a universe where the dark matter density just happens to fall within a narrow, habitable window. Too much dark matter and its intense gravity would have crushed galaxies before they could properly form. Too little, and the gravitational scaffolding would have been too weak for stars and planets to ever coalesce from the primordial gas. In this view, our universe is not special, just lucky. We find ourselves in a cosmos with just the right amount of invisible sculptor to build galaxies, forge stars, and eventually allow for life to emerge and ask these very questions. This connection, while currently untestable, reframes the entire dark matter problem. The search for this invisible substance is no longer just about finding a missing particle within our universe. It becomes a potential window into the wider meta-universe, a clue that might reveal not only why our cosmos is the way it is, but also what other impossible realities might be floating in the vast beyond. This cosmic puzzle is not just for those in white lab coats. The search for the invisible sculptor has thrown open its doors, inviting the global public to join the hunt. Anyone with a computer and an internet connection can now contribute to cutting-edge cosmology through projects like Einstein at Home. This initiative allows you to donate your computer's idle processing power, creating a distributed supercomputer that sifts through mountains of data from gravitational wave observatories and radio telescopes. While you sleep or work, your machine might be the one to identify the faint, rhythmic spin of a pulsar hidden within the noise, a discovery that could provide crucial new clues about the behavior of gravity and dark matter in extreme environments. This collective effort turns millions of personal devices into a single, powerful instrument for discovery. The engagement extends far beyond distributed computing. Planetarium domes across the world now glow with visualizations of the cosmic web, immersing audiences in the hidden architecture of the universe. Award-winning documentaries bring the stories of scientists like Vera, Rubin, and Fritz Zwicky to life, while popular science books translate complex theories into gripping narratives of cosmic detective work. These mediums do more than just educate. They ignite a sense of shared wonder and curiosity about our place in the cosmos. This broad public support is not a mere side effect. It is a fundamental pillar of the endeavor. Solving a mystery as profound as dark matter requires decades of sustained investment, both intellectual and financial. It demands a societal commitment to exploring the deepest questions, a recognition that understanding the invisible forces shaping our universe is a human pursuit, not merely a scientific one. The collective awe inspired by a planetarium show or the quiet contribution of a home computer forms a crucial part of the foundation upon which giant telescopes and deep underground labs are built. It is a powerful reminder that the cosmos, in all its visible and invisible grandeur, is a story that belongs to all of us. Our very atoms are cosmic outliers. The matter that forms our bodies, our planet, and every star we can see in the night sky is the exception, not the rule. This fact carries a profound and humbling weight. For all of human history, we have believed that the universe was built from the same stuff we are. Now we know we are the rare, luminous flotsam adrift in a vast, invisible sea. This realization forces a deep philosophical shift. What does it mean to truly see or to truly know? Our eyes and our instruments are tuned to a narrow band of reality, completely blind to the dominant substance that surrounds us. We are like beings who can only perceive the foam on the crest of a wave, entirely missing the immense, dark ocean that gives it form. This challenges the very foundation of empirical knowledge, reminding us that our perception is not the final arbiter of what is real. The ethical dimension is equally striking. The quest to find dark matter consumes immense resources, funding sprawling laboratories deep underground and colossal telescopes on remote mountaintops. This is pure, fundamental research, driven by curiosity with no promise of a practical payoff. Yet, time and again, such journeys into the unknown have yielded unexpected treasures. The very World Wide Web was invented at CERN to help physicists share data. The development of medical CT scanners relied on technology first created to detect antimatter. The relentless push to detect the undetectable forces us to invent new technologies, to create purer materials and more sensitive sensors, innovations that inevitably ripple out to benefit society in unforeseen ways. But the deepest value of this search may be the most human one. In a world often focused on immediate needs and short-term gains, the pursuit of dark matter stands as a monument to our species' unique drive. We are not content to simply exist within the cosmos. We are compelled to understand it, to unravel its deepest mysteries even when they offer no tangible reward. This quest to comprehend our origins and the hidden architecture of reality is a defining human trait. It is what transforms us from inhabitants of a world into conscious participants in a grand, cosmic story, forever reaching beyond the veil of the visible to ask what else is there. The relentless search for an invisible particle has forced us to invent a new kind of technology. To catch a ghost, you must first build a perfect trap, and that demand for perfection has sent ripples of innovation far beyond the walls of physics laboratories. Consider the quest for ultra-pure materials. To shield their detectors from the faintest background noise, scientists needed metals so clean they were virtually free of natural radioactivity. This pushed material science to its absolute limits, leading to new methods for refining copper and other metals to a purity once thought impossible. These radiopure materials are now finding uses in the most sensitive medical implants and diagnostic equipment, where even trace contaminants can skew results. The same goes for the sophisticated photon detectors developed for experiments like LUX Zeppelin. These sensors are so sensitive they can count individual particles of light, a capability that is revolutionizing medical imaging. Imagine a PT scanner that can see deeper into the human body with unprecedented clarity, all thanks to a technology honed in the hunt for dark matter. The data deluge from these experiments has been another engine of progress. Every day, these detectors generate petabytes of information, a chaotic ocean of digital noise in which a true dark matter signal would be a single, unique whisper. To find it, scientists had to create entirely new algorithms for pattern recognition and signal processing. These powerful data sifting techniques did not stay confined to cosmology. They were quickly adopted by Wall Street to spot subtle market trends, by cybersecurity firms to identify novel malware hiding in network traffic, and by tech companies to improve everything from search engines to speech recognition. This is the beautiful, unintended consequence of pure curiosity. The drive to comprehend the cosmos does not exist in a vacuum. It forces us to stretch our technical and intellectual capabilities, creating tools and methods that then filter down into our everyday world, improving healthcare, securing our digital lives, and powering the global economy. The invisible sculptor, it seems, is not just shaping galaxies, but quietly guiding the very trajectory of human innovation. This global hunt for an invisible particle is one of humanity's most ambitious collaborations. From a mine in South Dakota to a mountain in Italy and a space telescope orbiting 1,000,000 miles from Earth, the search for dark matter unites scientists across every border. These are not solitary endeavors. The LUX Zeppelin experiment in the United States, the Xenon project in Italy, and the upcoming Supersymmetry in Canada are all powered by international teams. Hundreds of researchers from dozens of countries contribute their unique expertise, from building ultra-pure detectors to writing the complex code that sifts through the data. This global partnership is not just beneficial, it is essential. The sheer scale and staggering cost of these projects, which can run into the hundreds of millions of dollars, are far beyond the capacity of any single nation. No one country could build the James Webb Space Telescope or the Large Hadron Collider alone. This shared pursuit forces a remarkable unity of purpose, a setting aside of geopolitical differences in the face of a cosmic mystery that belongs to all of us. The engine of this cooperation is a deeply ingrained culture of open communication. At major international conferences, competitors in the race to make a discovery freely share their latest results, their most recent null signals, and their plans for future detectors. This transparency accelerates progress for everyone, ensuring that the entire field learns from every success and every failure, avoiding costly duplication of effort. Data-sharing agreements allow a scientist in Japan to analyze information collected deep under a mountain in the United States, bringing a fresh perspective to a stubborn problem. This model of international science is a powerful testament to our collective potential. It demonstrates that humanity is at its best when focused on a grand challenge that transcends nationality, working together not for territorial gain, but for a deeper understanding of our shared universe. One of the biggest confusions lies in the nature of antimatter. It is not dark matter. Antimatter is a form of ordinary matter, made of particles that are essentially mirror images of the ones we know. An electron's antimatter counterpart, the positron, has the same mass but a positive charge. When matter and antimatter meet, they annihilate in a flash of energy, but they both belong to the familiar world of atoms and light. Dark matter is something else entirely, a different class of substance that does not annihilate with ordinary matter in this way and remains fundamentally invisible to our entire electromagnetic spectrum. Another common mix-up conflates dark matter with dark energy. This is a case of two cosmic mysteries sharing a similar name but having opposite effects. Dark matter is the ultimate gatherer. Its gravitational pull acts as a cosmic glue, pulling galaxies together and building the large-scale structure of the universe. Dark energy, in stark contrast, is the great repeller. It is the mysterious force causing the expansion of the universe to accelerate, pushing galaxies apart over vast distances. One force builds cosmic cities, while the other is stretching the space between them at an ever-increasing rate. You might also wonder if dark matter is simply made of black holes. While an intriguing idea, observations have largely ruled this out as the primary answer. If the cosmos were filled with enough black holes to account for all the dark matter, we would see their gravitational influence more frequently through an effect called microlensing, where their gravity briefly magnifies the light of background stars. Our surveys have not seen nearly enough of these events. Primordial black holes, hypothetical relics from the Big Bang, could still account for a small fraction of dark matter, but they cannot be the whole story. Perhaps the most persistent misconception is that dark matter is a failing theory, a placeholder for our ignorance. Nothing could be further from the truth. The evidence for its gravitational influence is not a single observation, but a chorus of independent lines of proof. We see its signature in the impossible speeds of orbiting stars, in the bent light from gravitational lensing, and in the precise blueprint of the ancient cosmic microwave background. The reality of its effects is as solid as any discovery in modern cosmology. The open question is not if dark matter exists, but what it is. Clearing up these confusions sharpens the real mystery, separating established fact from the thrilling frontier of the unknown. No single scientist holds the key to this cosmic lock. The search for dark matter is a symphony of disciplines, each playing a crucial part in a grand collaborative performance. Particle physicists compose the theoretical melodies, dreaming up new particles and calculating their potential signatures in the language of quantum fields. Their ideas are then handed to the engineers and nuclear physicists, who perform a kind of technological alchemy. They design the heart of the detectors, turning theories of ultra-pure materials and sensitive sensors into physical reality, building machines that can listen for a ghost's whisper. Meanwhile, high above in the thin air of mountaintops and in the silent vacuum of space, astrophysicists act as the universe's observers. They meticulously chart the rotation of distant galaxies and map the faint glow of the cosmic microwave background, gathering the observational evidence that defines the mystery itself. All of this data, a deluge of information from colliders, telescopes, and underground labs, flows into the hands of computer scientists. They write the complex algorithms that sift through the cosmic noise, searching for the one in a billion pattern that could be a signal. And overseeing this entire process are the cosmologists who build digital universes inside supercomputers. They take the theories from the particle physicists and the data from the astrophysicists and run the ultimate test, simulating 13.8 billion years of cosmic evolution to see if their virtual universe grows up to look like our own. This is the very definition of modern big science, where the old boundaries between astronomy and particle physics, between engineering and computer science, have completely dissolved. The solution will not emerge from a solitary genius in an isolated lab. It will be born from the friction and synergy of these different minds working in concert. a testament to the fact that the universe's deepest secrets are too complex for any one branch of knowledge to unravel alone. Our journey through the shadowy realm of dark matter has revealed its role as the fundamental architect of the cosmos, from binding individual galaxies to weaving the vast cosmic web. We have seen its ghostly hand in the impossible speeds of orbiting stars and felt its immense weight in the way it bends the light from distant galaxies. The ancient afterglow of the Big Bang itself carries its indelible signature, confirming that this invisible substance was present at the very beginning, setting the stage for everything to come. For nearly a century, from Fritz Zwicky's first calculation to the silent watches in deep underground labs, we have been piecing together the evidence for this unseen cosmos that surrounds us. We have followed the hunt from colossal particle colliders trying to create it to space telescopes scanning for its annihilation glow, a global effort spanning disciplines and nations. The true identity of the dark matter particle remains one of science's most profound mysteries, a ghost that has so far eluded every trap set for it. Yet this long search has been far from fruitless. The relentless drive to detect the undetectable has pushed technology to breathtaking new frontiers, yielding purer materials, more sensitive sensors, and smarter data algorithms that benefit us all. It has forged a model of international cooperation, uniting thousands of minds in a shared, transcendent goal. This quest challenges us to look beyond our senses, to accept that the universe is built from something we cannot see, and to trust in the power of curiosity and reason to illuminate the darkness. As Carl Sagan once said, somewhere, something incredible is waiting to be known. The invisible sculptor is still at work, its secrets promising to reshape our very conception of reality. If you enjoyed this exploration into the cosmos's hidden depths, we invite you to subscribe for more journeys into the unknown. We would love to hear your thoughts on this grand mystery in the comments.